Let me show you something fascinating about your Android system, something that's been hiding in plain sight. Do you see this? Every single app on this Android device, settings, launcher, system UI, the phone app, they all have the same parent process ID 342. That process is called Zygote. Zygote is the biological parent of every single app running on Android. When an app crashes and dies, Zygote is still there. When a new app launches, Zygote gives birth to it through a process called forking. Today we are going inside Android's most critical process, the one that makes your apps start in under 2 seconds instead of 10. We are diving into the source code, watching it work in real time, and understanding why it's one of the Android's most brilliant architectural decisions. Welcome back to Android Internals from Scratch. We are from Must Electronics. If you have been following along from episode 1, you know we have been systematically building our understanding of Android from the ground up. We have built Android from source, flashed it to the Raspberry Pi 4, understood the boot sequence, and in episode 10, we dove deep into the init process and Android's PID 1. In episode 9, we saw the complete boot sequence. Let me recap that quickly because it's crucial for understanding today's topic. When Android boots, the kernel starts and launches init as PID1. Init reads init.zygote64.rc. Init starts Zygote. Zygote preloads the framework. Zygote forks SystemServer. SystemServer starts all framework services. Apps can now launch. But we left some big questions unanswered. Why does Zygote exist in the first place? What does preloading the framework actually mean? How does forking work and why is it so fast? How do apps actually get started from Zygote? By the end of this episode, you will understand Zygote at a level that most Android engineers never reach. Let's start with the fundamental problem that Zygote was designed to solve. Imagine you are designing Android from scratch. A user taps an app icon, let's say Gmail. Your job is to start that app's process. How do you do it? On traditional Linux system, you use two system calls, fork and exec. Fork creates a copy of the current process. exec replaces that copy with a new program. This works great for traditional Linux programs like ls or grep, but Android apps are different. If you had to do all of this from scratch every time someone launches an app, then starting Gmail would take 8 to 10 seconds. That's completely unacceptable for a mobile device. Google's Android team needed a solution, and they found it in a concept from biology. In biology, a zygote is the first cell formed after fertilization. It contains all the genetic material needed for a complete organism. That cell divides through a process called mitosis. Each new cell gets a complete copy of the DNA. Android Zygote works on the same principle. Here's the genius of it. Instead of initializing the framework from scratch for every app, we do it once in Zygote at boot time. Then, when an app needs to start, we fork Zygote. The new process inherits all the preloaded code instantly through a Linux kernel feature called copy on write, from 8 seconds to 400 milliseconds. That's a 20x improvement. This is why Android feels responsive. Now let's see exactly how this works in the actual source code. Let's navigate to Zygote source code. Remember, we downloaded the entire AOSP tree back in episode 4. This directory has all the Zygote Java code. Let's see what we have got. 9 files. Let me break these down. There are 4 main files, the big ones that do the heavy lifting, and 5 supporting files. The 4 main files are ZygoteInit 40 kilobytes. This is the entry point where the main method lives. Zygote 65 kilobytes. The core forking logic, the biggest file. Zygote server 26 kilobytes. The socket server that listens for app launch requests. Zygote connection 27 kilobytes, handles each individual fork request. Together, that's about 158 kilobytes of core logic. The other 5 are supporting classes. Zygote arguments passes command line arguments. Zygote command buffer buffers commands from the socket. Zygote config configuration settings. Zygote connection constants protocol constants. Zygote security exception custom exception class. We will focus on the 4 main ones because that's where the action is. Let's start with ZygoteInit.java. This is where everything begins. This command tells us exactly what Zygote does. Pre-initialize classes, wait on a Unix domain socket for commands, fork child processes that inherit the initialized state. Let's see how init starts Zygote. Remember this from episode 10. Init executes system bin appprocess64 with the Zygote flag. This native binary eventually calls into Java and invokes ZygoteInit.main. Three critical steps in Zygote's main method. Preload. Load all framework classes and resources into memory. Fork system server. Create the first child process. Listen. Enter an infinite loop waiting for app launch requests. Let's dive deep into each one, starting with preloading. This is where the magic happens. Preloading is where Zygote's performance benefits come from. Let's look at the preload method. Multiple preload steps. The most important one is preload classes. Let's see what it does. The key line is class.forName. This loads each class into memory and initializes it. But where does the list of classes come from? It reads from a file called preloaded classes. Let's see that file. Over 7,000 classes. Let's see what's in there. These are all the Android framework classes that every app might use. Activity, Weave, Text Weave, Context, Intent, Bundle, and thousands more. By loading them once in Zygote, every app that gets forked inherits them immediately. Now here's the key question. How long does this preloading take? Let's look at the actual boot logs from our Raspberry Pi. Look at these numbers. 17,139 classes loaded in 1657 milliseconds. That's 1.6 seconds. Resources loaded in 60 milliseconds. The total preload time is just over 2 seconds. This happens once at boot. Every single app launched after this inherits all these preloaded classes through Linux copy on write memory. We'll prove this with memory analysis later. After preloading, Zygote needs to fork its very first child process, that is SystemServer. Let's see how that works. Remember from episode 9, SystemServer is the process that runs all of Android's framework services. Activity Manager, Window Manager, Package Manager, everything. But SystemServer isn't a special process. It's just the first app forked from Zygote. This is textbook Unix process forking. The fork system call creates a copy of the current process. It returns 0 in the child process, the child's process ID in the parent process. So after this fork, there are two processes running. Zygote the parent continues executing and returns null. System server the child sees PID equal to 0 and calls handle system server process. Let's verify this on our running Raspberry Pi. There it is. System server has PID 730 and its parent process ID is 343, which is Zygote 64. This proves that system server was forked from Zygote. Now let's check the timing. When did Zygote start and when did it fork system server? Zygote started at 16.639 seconds. It forked system server at 22.506 seconds. That's about 6 seconds of preloading before forking. And immediately after forking system server, you see that last line, accepting command socket connections. This is where Zygote enters its listening mode. After forking system server, Zygote's job is to wait for app launch requests. It does this through a Unix domain socket. Let's see how that works. Zygote listens on a Unix domain socket for app launch requests. Let's see that socket. Two sockets, because the Raspberry Pi supports both 64-bit and 32-bit apps. When you tap an app icon, here's the entire flow. This entire process from tap to visible app takes about 1.5 seconds. Let's see the source code that handles this. This is a classic event loop. os.poll blocks until someone connects to the socket. When Activity Manager sends a fork request, process command handles it. That method reads the request parameters and calls the actual fork. Let's see this happen live. Let's launch an app and watch Zygote fork it in real time. I'll use the Settings app for this demonstration. Settings is already running from earlier. Let me kill it first to simulate a fresh cold start. Good, it's gone. Now let's launch it and measure the startup time. The am start command with the W flag will wait and report timing. Cold start in 1656 milliseconds, around 1.6 seconds. This is the power of Zygote forking. Without Zygote's preloading, this would take 8 plus seconds. Now let's verify that settings was forked from Zygote. PPID 343. Zygote is its parent. Now let's look at all the apps currently running and verify they are all Zygote's children. Look at that PPID column 343, 343, 343. Every single app is a child of Zygote. System UI, network stack, phone, settings, launcher, keyboard, all of them were forked from PPID 343. This is beautiful. Every app on Android shares the same ancestry. They are all siblings, born from the same parent process. Now let's see how the forking actually works at the native level. We have seen the Java side of Zygote, but the actual fork system call is native code written in C++. Let's look at it. 123 kilobytes of native code. This is the JNI, Java Native Interface, bridge between Java and C++. Let's find the fork function. This native function receives all the parameters needed to create the new app process. UID and JID, that is user and group IDs, runtime flags, SC Linux security context, nice name, that is process name you see in PS, file descriptors to close. Let's see what happens inside. There it is, the actual Linux fork system call. This creates a new process by duplicating the current one. After the fork, in the child process, that is the new app, functions performed are close Zygote socket, release mutex locks, prepare for specialization. In the parent process, that is zygote, functions performed are release logs, return the child's PID, go back to listening on the socket. After forking, the child process goes through specialization. That's where it sets its UID, applies SLNX context, mounts storage, and becomes a real app instead of a zygote clone. So now we understood how apps are forked. But why is this so fast? The answer is copy on write memory sharing. Let me prove it to you with actual memory measurements. Linux has a feature called copy on write. When you fork a process, the child doesn't get a full copy of the parent's memory immediately. Instead, both processes share the same memory pages. Only when one of them writes to a page does the kernel make a copy. This saves enormous amount of RAM. Let's measure this. I'll use dumpsys meminfo to check memory usage of different processes. Here PSS stands for proportional set size, which is real memory used by this process. RSS stands for resident set size, which is total memory mapped into this process. The system server uses 173 megabytes of PSS but 341 megabytes of RSS. That's more than double. The difference is shared memory. System UI 86 megabytes PSS, 248 megabytes RSS. Again, RSS is almost 3x higher than PSS. That difference is shared with other processes. Let me put this in perspective. Let's say the preloaded Android framework takes 100 megabytes of RAM and you have 30 apps running. Then without copy on write, it would take around 3000 MB. And with copy on write, it will take 100 MB. So this saves 2.9 GB of RAM. That's why Android can run smoothly on devices with just 2 to 4 GB of RAM and still keep dozens of apps in memory. The framework classes preloaded by Zygote are shared across all apps through copy on write. This is the brilliance of Zygote. It's not just about speed, though it makes apps launch 20x faster. It's also about efficient memory usage. Android can keep more apps resident in memory, which means better multitasking and faster app switching. Okay, let's recap what we learned because we covered a lot. Zygote exists to solve the cold start problem. Starting an app from scratch would take 8 seconds. Zygote preloads everything once and then forks copies. It preloads 17,182 framework classes in 1.6 seconds at boot. Every app is forked from Zygote. We proved it. Every app has PPID 343. System Server is Zygote's first child. PID 730, PPID 343. Apps launch via a socket. Dev socket Zygote. Activity Manager sends requests. Zygote forks. The actual fork happens in C++ through JNI. COM Android internal OS zygote.cpp. And copy on write memory sharing saves gigabytes of RAM. Apps share the preloaded framework. We went from theory to source code to live demonstrations. We watched an app launch in real time. We measured memory. We proved parent child relationships. But remember, Zygote's first child, System Server, PID 730. We saw it get forked, but we didn't look inside it. What does System Server actually do? Why is it so important? That's episode 12, System Server, the heart of Android. System Server is where all the Android framework services live. Activity Manager, Window Manager, Package Manager, Power Manager, every service you have heard of runs inside System Server. We are going to see what happens inside that process. How it starts 80 plus services in phases. How it manages the entire Android framework. This is where Android truly comes alive. If you have made it to episode 11, you are in rarefied air. Most Android developers never learn this stuff, but you are doing it. You are understanding the system from the ground up. Questions, comments, confusions, drop them below. We'll read every single one. If this video was useful, please like the video and subscribe to Must Electronics.